Welcome class to the Math 1030 video for Unit 6C, the normal distribution. Okay, the normal distribution is the distribution of data across a graph, and normal has several characteristics. So I'm going to draw a visual of the normal distribution first. So we have our graph axes, okay, and we have the frequency on the vertical axis. And our curve is going to be nice and symmetrical. It's like a hill. We'll zoom in there a little bit. Okay. And it is symmetrical around the mean. Okay. So I'll put the mean here. All right. So all the data is distributed around the mean. Okay. A couple of other things about it is that there is little bit of data on the small frequency of data on the left here, right here. That's going to be called a tail. And a little bit on the right, which are the higher values. Another tail. Most of the data is in the middle, around the mean. Okay. So that's a normal distribution, where the frequency is around the average, the mean, the most of the instances of data. So let's go ahead and think of a few examples of data. You can have data about attributes about people or objects. So for example, people, if you find the heights of the average adult, or all adults, okay, things like that, adult heights, baby weights, okay, those ones have most of the babies weigh around a mean or an average, and then there's some that are really small, some that are really big. Okay, so you can do something like in manufacturing, the normal distribution is seen a lot, where we can say, like, when they strike coins, for example, they manufacture coins, so their weight and size of coins, okay, follow a normal distribution, because coins are intended to be the same size and weight, but there's very minute differences between each actual strike. And so when they are manufactured, there's some that are smaller and some that are larger than what the intended weight is. Okay, so weight of coins is one. Things like in manufacturing, like a truck weight. Okay, trucks weigh of a certain kind of truck. They will vary a little bit based off of little differences in their manufacturing. A couple other ones are auto prices. Okay, you given a certain kind of car, it will cost a certain amount on average. Okay, some of the versions of the car will be a little bit less, some will go for a little bit more. Okay, so auto prices follow a normal distribution. And the other big one is class tests or assignments. Okay, so most people will get a C and average, and then there's going to be a few A's, and there's going to be a few F's. Okay, so they all kind of cluster around the mean. Okay, so those are examples, real life examples of a normal distribution of data. So the data set satisfies the following 4 criteria for a normal distribution. So more specifically, we have 4 criteria here, and the first one is most data values are clustered around near the mean. Most data values are clustered near the mean. Giving a distribution. Giving the distribution a well-defined peak. Okay, so it's a single peak, so there's no like bimodal things. Okay, number 2, the data values are spread evenly around the mean, making the distribution symmetric. Larger deviations, number 3, larger deviations from the mean become increasingly rare, producing a symmetric tapering tails in the distribution. Larger deviations, so as you go smaller and as you go larger, okay, those deviate from the mean, they become increasingly rare, meaning the frequency is not as much. Okay. So producing the symmetric tapering tails. Of the distribution. Okay. Number 4, the fourth one, is that individual data values result from a combination of many different factors, such as genetic and environmental factors. Okay, so there's a lot that goes into these data points. Okay, so genetic factors are like, for humans, adult heights. So if your parents were tall, then you were likely to be tall. Environmental factors could be something like when you strike coins or produce screws or truck weights, some differences in the environment where the object was manufactured could affect the actual size, however minuscule. Here's a couple of examples. What situations are likely to have a normal distribution? Scores on a very easy test, or foot lengths of a random sample of adults. Okay, so if the scores are on are on a very easy test would not have a normal distribution. Because if the test was very easy, then everybody would score well. Okay? And then they would have most people scoring higher than everybody else. So that would skew the nice symmetric curve. Okay? So for part 1, no, it is not symmetrical because if the test was easy, then everyone would get the correct answers. There would be no like middling ground. Everybody would just get A's. Foot lengths of random sample of adults. So if you randomly sample adults and you get their foot length, it's like their adult height or baby weight, where you'll have a normal distribution. Because most people's feet are around the mean, and some people are smaller, some people are larger. So relatively few are smaller, relatively few are larger. Because most people have an even spread. Okay, so that would follow our normal distribution. We're going to now look at what the book refers to as the 68, 95, 99, 7 rule. Okay, so we need to approximate the data spread using the standard deviation around the mean. So when we go above and below the standard deviation, like for example, 1 below the standard deviation from the mean, 1 above the standard deviation from the mean, we have this area here. Okay, and this area is going to be under the data points curve. Let's go purple. Okay, under the data points curve. And so that when we just take a look at 1 standard deviation below to 1 standard deviation above the mean, we find that 68% of the data values fall within that area. Okay, so that's what it says about right here. 68% of the data values fall within 1 standard deviation of the mean. Okay, and when we go out to 2 standard deviations above and below the mean, we're at 95% of the data values. Okay, and so that's this one right here. 2 standard deviations below, 2 standard deviations above, and here's the mean. So we have this range right here. And this range right here represents 95% of the data. Okay, so that's what our graph is saying right there. And when we go to 3 standard deviations above and below the mean, we're at 99.7% of the data. We cover 99.7% of the data. Okay. When we do this, 3 standard deviations below, 3 standard deviations above. So we're within 3 standard deviations. So that's like pretty much all the data. So we have a nice way to characterize where the data is at 3 points, 68, 95, and 99.7%. One good application, so what can we do with that? One good application is to look at SAT scores. Okay? So in our next example, we have our normal normal distribution, and we look at SAT scores. SAT scores are set so that the mean is 500, so the average student score from their raw score is scaled to 500. The standard deviation is 100. Okay. So the mean is 500, the standard deviation is 100. Okay. So when we take a look at the data, we can say that 68% lie between 400 and 600. So most people get 400 to 600 on their SAT score. 95% lie between 300 and 700, and nearly everybody, the range for nearly every score on the SAT is 200 to 800. 800, I think, is the max. So let's take a look at one thing that we can also say. We can also say that given that this distance right here from this point to this point is 68%, as we see here, we can also say that there's a certain percentage from this point to this point. Okay? This point spans a part of the area curve, or area under the curve, or the curve that is not labeled, but we can deduce the amount of students who score between 500 and 600. Or the percent, I should say. More technically, it's the percent. Percentage of students who score between 500 and 600. All we have to do is take that 68%, and we're only looking at half the interval. So we take the 68% and divide that by 2, okay? And we get 34%. So 34% of the students score between 500 and 600 on the test. In part C here at the bottom, we are going to find out some percentages of scores that are in various parts of our graph. So like greater than 600 or less than 400 or greater than 700. And so we can deduce all of these by using the percentages. So we're going to kind of just take a span look here at each of the percentages and what they need to do to make up 100%, so that we can see how many people scored greater than 600 or so on. So I'll draw out what I mean here. So we know that this distance right here, which I'm following this part right here, is 68% of the data. Okay, this is 68%. We know that this part right here, the blue part, goes all the way till the end of our data set. So put an arrow here. And then this red part make up the difference between 100% and 68%. Okay, and so we know that just by quick calculation that 100% minus 68% is equal to 10 minus 2, 9 minus 6 is 3, 32%. Okay? And so we're going to split the 32% on the red and the blue parts, which means that 16% is going to go here, okay, from 600 on to the very end, and from below 400 is also 16%, because it was the difference between 100% and 68% is split. Okay. All right, so let's take a look at another type of scale. We're going to go ahead and use green. Then the other area that we can kind of deduce across the spectrum here is the 95% area. 95% span right here. Okay, so 95% of the data lies here. So from this part here to this part here. Okay, we span our 95%. And we're going to use yellow. So that means that from 300 to 700, 95% of the people scored those scores. Above 700 and below, it's purple, and below 300 will span the rest of the data set from 95, which means that we know that 5% has to be split between two parts. Okay, so this right here is 2.5%, and that's below 300, and this above here is 2.5% as well. Okay, and our third span that we're going to look at is the 99.7% span, and we'll use orange to do that one. Okay, so 99.7 goes from here, right at the 200, all the way out to here at the 800. Okay. This right here is 99.7% of the data. Okay, and so we'll use cyan to say that from 99.7 to the end is the difference between 99.7 and 100% is 0.3%, so we can split that into 0.15%. And we'll use kind of pinkish color for this one, rose color. That also be 0.15%. Okay, so we split the 0.3 in half, 0.3% in half. Okay, so we have our data split in 3 different ways according to our standard deviations. Okay. And we've calculated the percent for each section of those 3 ways. Now let's take a look at what percent of the scores. What percent of the scores are greater than 600? Okay, that's our first one, number 1. Greater than 600, so that's this part right here. Greater than 600 is the blue arrow, which we're going to do 16%. Okay. Which percent of the data is less than 400? That's this part of the blue, of the red arrow of the first split. That's 16% as well. Because they mirror each other, okay? That's symmetric. Which part is greater than 700? Okay, that's this part right here in the yellow, greater than 700. Okay, so 2.5%. Which part is less than 300? That's this part right here, less than 300, another 2.5%. Which part is greater than 400? Greater than 400. Well, we've divided it up into some good ways here. Greater than 400 is this part right here, going on to the end that way. That correlates with these 2 parts, the purple section and the blue section. Okay, 68 and 16%. So we'll add those to get the percentage scores that's greater than 400. So we have 68% plus 16% is equal to 84%. Okay, so 84% is greater than 400. Which part is less than 700? Less than 700 is this distance right here, from here all the way down to the end. And that's the same as the 95 and the 2.5 right here. The green and the purple. So green and purple is 95% plus 2.5% is equal to 97.5%. Okay, so that is so what does that mean in context again? 97.5% of the students scored less than 700. What percent of the students scored greater than 300? Okay, so again, we're looking at this 300 and forward to the end. And that's this part right here, 95 and 2.5%. So the green part and the yellow part. So we'll add those together. And it's the same as the part Roman numeral 6 because it's symmetrical again. Okay, so we have 97.5% here. Okay, so those are our ways to divide up the normal distribution to see what percents are greater than 400 or less than 700 or greater than 200, anything that we want to look at. So a little bit more diverse there. Okay. We're going to take a look now at standard scores and percentiles. So let's say that we want to take a look back at our scores on the SAT. Let's say that we know that the percent below 400 was 16%, right? From 400 down below. So if you scored a 400 on the SAT, you'll score better than 16% of the people. But what happens if you want to know a percent that you scored above, let's say something that's not on the nice 100s of the scale here. Like let's say 450. If you scored a 450 on the SAT, did you score above what percent of the people did you score above? Okay. And so that's where we're going to get standard scores from. Standard score or z-score is from the standard deviation, okay? So notice that 450 is between halfway between one standard deviation below the mean. So it's like half of a standard deviation below the mean. Okay, so what is the percent of that score scored above how many people? So we're going to see the standard score here. And we're going to say, well, what is the standard score? A more concise definition is the number of standard deviations a data value lies above or below the mean. Okay, so where does it lie? Where does any number score lie? So how do you calculate the z-score for a score of, say, 650 on the SAT? Okay, so we can see how many standard deviations it is above or below the mean, and then we can see what percent of the people scored above it and below it. So we're going to use a formula. Okay, the z-score formula the z-score or the standard score. Okay, note that we're doing standard here, standard deviation and standard score. Okay, so that's the connection there. The z-score or the standard score is equal to the data value subtract the mean divided by the standard deviation. Okay, that's z-score. And so we're going to do the z-score for 650 SAT. Okay, so z-score is equal to the data value, which is 650. Subtract off the mean. The mean was set at 500, divided by the standard deviation, which was set at 100. So that's going to be 150 over 100, which is equal to 1.5. Okay. What does this 1.5 mean? It's 1.5 standard deviations above the mean, since 650 is greater than 500. Okay, so we'll write that down. Okay, so that's what the 1.5 is. Okay, so let's go back to our table here for SAT scores. 650 lies right here. Okay, and so it is halfway between 1 standard deviation above the mean and 2 standard deviations above the mean. Okay. Okay, so next we're going to talk about percentile. If you scored a 650, how many people scored above you? What percent? Or what percent scored below you? That's what the percentile will be. The percentile of a data value is the percentage of all data values in a data set that are less than or equal to it. The percentile of a data value is the percentage of all data values in a data set that are less than or equal to it. Okay, so percentile is a percentage that has more to it. So let's take a look at this z-score table. Okay, so we look at our standard deviation 1.5 above the mean for our score of 650. And I'm going to zoom in on 1.5. Okay, here's 1.5. And it corresponds with 93.32. Okay, so the percentile of a score of 650 on the SAT, so part E here, means that an SAT score of 650 has a z-score of 1.5. In the table, 1.5 corresponds with 93.32. Percentile. So it's a 93.32nd percentile. Okay. It means that 93% of the students taking the SAT scored below 650. Okay. All right, so percentile is the percent at and below what the score is, or what the data point is. Let's take a look at one more thing. What percent of the students taking the SAT scored above 750? Okay, so what we need to do to calculate that is the key is above, so not below. The percentile is all catered to below a score. So we can take, our main goal then is to find the z-score of 750, then find the percentile of 750, and then subtract that from 100% to see how many score above. Okay, so number one, find z-score of 750. Z-score is equal to 750. Subtract 500, so the data point minus the mean, divided by the standard deviation. So that's equal to 250 over 100. It's equal to 2.5. Okay, z-score, 2.5. So 2.5 standard deviations above the mean. That's the z-score. Okay, so we found that. The next step is to find the percentile. Again, the percentile is the percent of the students that scored below that z-score, below that standard deviation. So percentile for 2.5, we'll zoom in here on our table, 2.5 corresponds with 99.38. Okay, so we find the percentile. At or below. Use the table. So 2.5 corresponded with 99.38 percentile. Okay. And so to find the third step was to find the percent above. So we take our 100%, subtract off our 99.38%, and we get 0.62%. So 0.62% of the students scored above 750. Okay, so that's our answer there. Okay, so there we go. That's our end of our section. Please let me know if you have any questions.